Ladies and gentlemen, welcome back again. We will soon start our session 8. This session is named Professor A.K.M. Shah Newaz Memorial Session. The session chair is Professor Abhishek Dhar from International Center for Theoretical Science, ISTS, Bangalore, India. So I am now requesting Professor Dhar to please proceed. Thank you.
Okay, thanks. So this session is in honor of Professor A.K.M. Shah Newaz, and I'll read out a note about him. So Professor Newaz is one of the best products of the Department of Physics, University of Dhaka. He did his bachelor's and master's in physics from here. He did his master's thesis on high energy physics. Professor Newaz did his PhD from sunny Stony Brook in semiconductor physics. He did his postdocs from Washington University in St. Louis, MI, and from Vanderbilt University, Nashville, TN. And then he joined San Francisco State University as a full-time faculty member. His research area became nanostructured materials, their physics and characteristics, related fabrications, etc. He has published 64 research articles in Nature Communication, PR Letter, PRB, Applied Physics Letter, Nano Letters, ACS, Journal for Physical Chemistry C, etc. Professor Newaz passed away last year in 2023. Professor Newaz was a good soul who touched a great many hearts and is missed at a very different level. So with this, now I would like to request Professor Ashok Sen to give his plenary talk.
Okay, thank you very much. And it's a great honor for me to be in this conference in honor of Professor S.N. Bose. And I would like to thank the organizers, and in particular Professor Kamrul Hassan, for inviting me and giving me this opportunity. Thank you. Now, unlike Professor Partha Ghosh, who had extensive interaction with S.N. Bose, I really didn't have that fortune, but I did have the fortune of meeting him for 5 minutes in my life. Okay. And that time I was in class 8 or 9. And one Sunday afternoon, my father told me that I'll take you to meet Professor S.N. Bose. And that I stood in total shock, because before that time, my world of people was divided into two kinds. So one who appear in books and the one who you meet. And there was no overlap between these two kinds of people. So anyway, my father took me to his house. I mean, it was a modest house. And as far as I remember, the door was open. There was only a curtain hanging. And as we entered, we found Professor Bose sitting on the bed, surrounded by some about 10 people. And it looked like a adda going on. So we stayed for a few minutes. And I don't remember what conversation we had. And that was my interaction with Professor Bose. But after that time, my two world of people merged together. And I realized that people who appear on books are also real people. And next time I saw Professor Bose was during his funeral procession. I remember that College Street was completely full and it was extremely crowded, and I had to somehow find my place in it. And we waited till the procession passed, and that was my last interaction with him. Okay, so with this, let me turn to my talk. Okay. So the talk today, as you can see, is titled Gravitational Wave Tales from Soft Theorem. Now this is a talk on classical gravity and may look somewhat inappropriate for this conference, because after all, Bose's work was about quantum statistics, right? So why am I talking about classical gravity? Okay. It's also not quite my field of research, which is quantum theory of gravity and string theory. Okay. Nevertheless, I hope that by the end of the talk, it will become clear that there is some connection between both this and what I do, quantum gravity, and Bose's work on quantum statistics. So let me begin by considering the kind of phenomena that we'll be considering in this talk. Okay. So let's imagine that there is a violent explosion in space, okay, where some stationary system just breaks apart into fragments. Okay. And during this process, it will emit gravitational waves. Okay. And if we place a detector D that's far away somewhere, okay, it will detect the gravitational waves at some later point in time. And the example of such violent explosion in space is, for example, supernova. One can consider also a more general situation, which is collision, okay, where instead of a single object exploding, we can have a set of objects that come together, interact and fly apart, and during this interaction it can possibly exchange mass, energy, momentum and other quantum numbers. Okay. And this process will also produce gravitational waves. Okay. And one example of such collision that is taking place in the universe right now is what is known as a bullet cluster, okay, which consists of a supercluster of galaxies that are passing through another supercluster of galaxies, each weigh about 10 to the 14 times the mass of the Sun, and the relative speed of these two clusters of galaxies is about 1% of the speed of light. Now, in general, if we want to compute gravitational waves that are produced during such process, it's a complicated process, okay, and it's complicated because of two reasons. Okay. The first reason is that when the objects are close, okay, they may undergo complicated non-gravitational interactions, okay, as in the case of explosion of a supernova, okay, because the nuclear forces play an important role in the whole explosion process. The second complication comes from the fact that gravity is described by nonlinear partial differential equations. Okay. So even if the interactions are purely gravitational, okay, like for example the case of merger of two black holes, where no other interaction plays any role, okay, the analysis is still complicated because you have to solve these nonlinear partial differential equations, and at present it's mainly numerical techniques that are used to find gravitational waves that are produced during such processes. It turns out, however, that some results in quantum theory of gravity, okay, which are known as soft graviton theorem, okay, can be used to get analytical results on some aspects of classical gravitational waves. Okay. And this is what is going to be the focus of this talk. Okay. So I'll describe in this talk the work done in various collaborations with these three people: Alok Ladha, who is a faculty member at Chennai Mathematical Institute, and Biswajit Sahu and Arnav Priya Sahab, both of whom are postdocs at present. Okay. And I should just say that most of this project has been pushed by Biswajit Sahu, okay, who in fact his thesis work was on this topic, and he wrote some single author papers, some papers with other graduate students, and he really has pushed this subject. Okay, so what I am going to describe today is the summary of all these developments. Okay. So let me begin with an introduction to what gravitational waves are. Okay. So we go back a little, we start with electromagnetic radiation. Okay. So let's recall that the electromagnetic fields can be described by what is called a four-vector, a four-component vector field, four-component field, whose zero component is the electrostatic potential, and whose 1, 2 and 3 components are the three components of the magnetic vector potential. And the usual electric and magnetic fields that we actually measure are related to time and space derivatives of this four vector field mu. And when charged particles interact and as a result accelerate, they will produce electromagnetic wave. Okay. And electromagnetic wave typically consists of, again, time and space varying electric and magnetic fields. Now, one particular feature that distinguishes an electromagnetic wave from, say, usual electrostatic potential or the potential due to a magnetic dipole, okay, is that if we go at a distance r from the source, okay, the electric and magnetic fields fall off as inverse power of r, and not, for example, as 1 over r squared as what happens for a electrostatic field, or 1 over r cube, which will happen for a magnetic dipole. So electromagnetic radiation has its strength falling off much slower than the electrostatic fields at large distance, and that's the reason why far away from the source, these are the dominant effects. The waves that are produced by the source, okay, those are the dominant sources of electric and magnetic fields away from the source. Now, gravitational waves or gravitational radiation are similar. So, in Einstein's general theory of relativity, a gravitational field is a symmetric two-index field h mu nu, and this measures distortion of space and time. So, the main difference between the electrostatic field and electromagnetic field and gravitational field is that electromagnetic field has 4 components, whereas a gravitational field has 10 components because it's a 4 by 4 symmetric matrix. And just like electromagnetic fields are sourced by charge, the gravitational fields are sourced by mass or energy. So the gravitational waves will involve time and space varying h mu nu, just as electromagnetic waves involve time and space varying a mu. And this time and space varying h mu nu can be measured by gravitational wave detector like LIGO, right, which basically measures distortion of space and time as a gravitational wave passes the detector. And the goal of a theorist in this picture is that for a given process, we want to compute what kind of gravitational wave signal should be produced at a faraway detector. Because then, once we make the measurement of h mu nu, we can try to reconstruct what event actually took place that gave rise to that signal. Okay? So the theorist the theorist's goal is to calculate h mu nu for a given process. So now let me set up some conventions, okay, which are all very familiar to for a physics student, but let me say it anyway. Okay. So I'll denote by c the speed of light. Okay. Capital G will denote the Newton's gravitational constant. I'll denote the space-time coordinates by 4 coordinates x mu with x0, x1, x2 and x3, of which x0 will be given by the speed of light times time, okay, where t is the usual time coordinate, and x1, x2 and x3 are the usual space coordinates. And similarly, I'll combine the momentum and energy into a 4-dimensional vector, 4 momentum p mu. So p0 will be energy divided by the speed of light, and p1, p2 and p3 are the usual momenta that a particle carries. I'll also introduce these 2 matrices, eta with lower index mu nu and eta with upper index mu nu. They are the same matrix, right? They are both 4 by 4 diagonal matrix with eigenvalues -1, 1, 1, 1. Then I'll introduce the inner product between 2 such 4 vectors, right, which is given here, right? Simply inner product minus a0 b0 plus a1 b1 plus a2 b2 plus a3 b3. And using this inner product, we can calculate the inner product of P and P, for example, P dot P, right, that's given by this. And now if you use the usual relation between momentum and energy, right, which you recall is E square equal to P square C square plus M square C to the 4, and substitute here, you will find that this P square is given by minus M square C square. Finally, 2 more conventions that will be useful for us, right, which again, this may not be completely familiar to even undergraduate students, that whenever an index is repeated, it's implicit that the index is summed over from 0 to 3. Okay. So if, for example, we write an expression like eta mu nu p mu, right, you see that in this product mu comes twice, right, once in eta mu nu and once in p mu. So it's understood that this means that the index mu is summed from 0 to 3, right. So this really means this. And the final convention is that given a vector with upper index, we can lower its index by multiplying by this matrix eta mu nu, and we can also raise its index by multiplying by this other matrix, inverse matrix eta upper mu nu. Okay. So if we follow this convention, then the upper and lower indices are related by this simple formula over here. Okay. I am saying this in detail because ultimately I will write down the various formulae in this convention so that it should become clear what the formulae mean. right? For example, if an index is repeated, it should be understood that that index is summed over from 0, 1, 2, and 3. Okay, so now let me first describe the summary of results. Okay, so the way the talk will be organized, it will first describe the summary of results, and then I'll briefly outline how these results were derived. Okay. So we go back to the situation that we started with. We consider a scattering in space, okay, where a set of objects of 4 momenta p1 prime to pm prime, they come together, they interact, and then they disperse as a set of objects with 4 momenta p1 to pn. Okay. So you see that the number of incoming objects and number of outgoing objects are not the same necessarily, because objects may fuse during this process, or some objects may split apart, right? There may be a nuclear explosion during this whole process, which just makes things fragment. Okay. So anything can happen during this process, right? We are not making any commitment to what happens during the scattering process. Okay. So here I have only drawn 2 incoming particles and 2 outgoing particles, outgoing objects, but in general there are multiple incoming objects and multiple outgoing objects. Okay. And in any process, it's useful to choose an origin of space-time. So we'll choose the origin of space-time to be inside the region where the scattering takes place, right? Which means that basically we'll assume that the scattering takes place somewhere around t equal to 0 and somewhere around x vector equal to 0. Okay, so that's my choice of what we mean by origin of space-time. So if once such a scattering happens, okay, it produces gravitational wave which propagates out, and imagine that you have a detector far away, right? This signal will reach the detector at some time t naught. So this t naught will be given first of all by r over c, that's the light travel time from here to the detector. R is the distance to the detector. Okay. But it turns out that there are corrections to this formula, okay, and the corrections come because gravitational waves as well as electromagnetic waves are affected by gravity. Okay. So there is a gravitational drag on the gravitational wave, and that slows it down a bit, right? So the actual time that the signal reaches the detector has a linear term in R, but there is also a logarithmic term, right? But we don't really need to know what these corrections are. And also note that the definition of t naught is somewhat arbitrary, right? You can always shift order, shift by constants, because when I said that the peak of the signal reaches a detector, right? I mean, it need not be that the signal has only one peak, right? It may have multiple peaks. So which peak do you choose? And the point is that it doesn't matter, right? That there is a limited time period where the signal, the bulk of the signal is passing the detector, and we choose the t naught to be some time in that time period. Okay, now we'll introduce what is called the retarded time at the detector, okay, u, which is t minus t naught. Okay. So what u measures is the time at the detector relative to the time at which the bulk of the signal reaches the detector. Okay. And our focus in this talk will be the form of the gravitational waveform, the h mu nu, at late and early time, right? Which means at large value of u, large positive or large negative value of u. Okay. Now, why do we focus on this? Because this is the contribution that we can say something useful about. Okay. So imagine that we have a detector, the signal passes the detector, we study the shape of the signal way before the actual peak arrives, okay, and way after the actual peak has passed through. Okay. And it's that part of the signal about which you will be able to say something analytic. Okay. So to specify the gravitational wave, we have to specify essentially h mu nu as a function of t, or as a function of u. Okay. But it turns out that it's easier to write the formula in terms of a slightly different quantity, which I'll call E mu nu. Okay. So E mu nu is defined here, right? These rho and sigma indices are summed over, because recall that I told you that any time an index is repeated, it's summed over. So rho appears twice in this product, sigma appears twice. So this really means sum over rho and sigma. Okay. But the point is that given h mu nu, e mu nu can be found, but it also goes the other way. You can reverse this equation and we can write an equation for h mu nu in terms of e mu nu. So if I tell you what e mu nu is, you can go ahead and calculate h mu nu, right? So you are not really losing anything by working with e mu nu instead of h mu nu. It's just the formula slightly simpler in terms of e mu nu. Okay, so here is the first result. Okay. That if we look at terms that are proportional to 1 over r, that means the radiation term, we don't worry about the Coulomb kind of term. Okay. Then E mu nu at early time, at large negative u, has this form. Right? It has an expansion, a constant C mu nu over u, then a constant G mu nu times u to the minus 2 log u, okay, and then there are higher order terms. And E mu nu at late time, that means large positive u, okay, has an expansion of this form, a constant, then a constant times 1 over u, and then again a constant times u to the minus 2 log u. Okay, and these constants are different from these ones. So the first result is that the u dependence has this particular structure. There is a 1 over u term, and then the next term is 1 over u square log u. The second point is that these coefficients that you see appearing here, okay, are given solely by the 4 momenta of the ingoing and outgoing objects without requiring any knowledge of the details of the scattering process. Okay. So you don't need to know if a nuclear explosion took place during that collision, right? As long as you know what went in and what came out, okay, you can compute and predict the values of all these constants. Okay. So it also can be reversed, that if we could measure all these constants, then these constants tell you something about a relation between the momenta that went in and the momenta that came out, right? Because that's really the goal of the gravitational wave detectors, that you want to detect a signal and then you want to reconstruct what happened. Okay, so these relations can help you reconstruct what happens. Okay, so in the next 2 slides, I am going to show you some formula, right? Those will be the formula for these coefficients. Okay, the formula will look complicated, but the details of the formula are not really important, right? What is important is the fact that those formulae exist, right? That, I mean, it's just to, I'm showing you the formula just to make you, to convince you that I'm not cheating you, that there are really formulae like that, right? Where you can write these constants in terms of the ingoing and outgoing momenta. So here are the formulae for A mu nu, B mu nu, and C mu nu. Okay, and I should also say that normally in our field, we often set the fundamental constants to 1, right, h bar and c, but here I have not set anything to 1, right, all the constants are explicitly visible, and you can see that there is no h bar anywhere here, right, which is not surprising because we are really talking about a classical physics, right. This is a classical gravitational wave that is produced by this classical collision process. Okay, and you see that these formulae involve only the momenta of the ingoing and outgoing particles. The only other things that it involves is the r, that is the distance to the detector, okay, and n is essentially the direction of the detector, right. N is a 4 vector whose first component is just 1, and then the other 3 components are x over r, the x vector over r, that basically tells you the direction cosine of the detector, where the detector is placed. Okay, but nothing else appears in this formula. Not even the angular momenta of the ingoing and outgoing particles, right? It's not that I have assumed that the ingoing and outgoing objects don't carry angular momentum. It's just that they don't appear in this formula. Okay, so here are the formula for F mu nu and G mu nu. Okay, they are even more complicated, and I mean, in order to fit them in, I had to use small fonts. Okay, but again, the important point is not that the formulae exist, but that what the formulae are, but the fact that the formulae exist. Okay, so now let me say a few words about the formulae, right? Some significance of what these various terms represent. So here is the formula for late and early time. You see that at late time, right, what it is saying is that the E mu nu goes to a constant. Now this is a somewhat surprising result, because what it is saying is that imagine that you have a detector, some gravitational wave comes, the detector starts oscillating, then you start seeing h mu nu. When the gravitational wave passes, even at when it has passed completely, large positive time, the gravitational wave signal, the h mu nu or e mu nu doesn't come back to 0, it comes back to a constant. This is in fact what is called the gravitational wave memory. This means that there is a permanent change in the state of the detector after the passage of the gravitational wave. Every time a gravitational wave is passing through, the detector gets changed, because the background has shifted. H mu nu is no longer 0. So this in fact was known, this effect was known since the 70s by work of various people in classical general relativity, but only in the last few years it was discovered by Strominger and his group that these are also related to what are called the Weinberg soft theorem, Weinberg soft graviton theorem. I'll make that connection later when I discuss this. These objects, the tail terms, the 1 over u and the 1 over u square log u term, are new. These are not calculated in classical gravity earlier, although now it has been calculated. These are first found using this quantum soft theorem that I mentioned earlier, and I'll describe later how quantum soft theorem connects to this classical physics. So these are really discoveries based on quantum soft theorem. Now this is a point I have emphasized, but let me emphasize again that all these constants can be expressed in terms of the momenta of the incoming and outgoing objects without knowing what forces operated and how the objects moved during the scattering. And this will be a consequence of soft graviton theorem. In contrast, if we have to compute h mu nu at finite time, it will depend on the details of the process, and will involve very complicated calculations. Typically it will involve numerical evolution, both because gravity is nonlinear as well as because the interactions that take place during this collision are complicated. There can be nuclear interactions, electromagnetic interactions, and so on. Now here is a technical point, but I thought I'll emphasize this anyway. That if we look at the expressions for these constants, these are the ones that captured these are the coefficients that appear in the final state, at late time. Then it involves a sum over final state particles, but this should also include integration over the outgoing flux of gravitational radiation, because gravitational radiation you should also think of as the final state particles, massless gravitons that are going out of the system. And this makes the use of this formula somewhat unsatisfactory, because this says that if you want to calculate this late time behavior of gravitational wave signal, you have to actually know what happened at finite time, because we have to calculate what kind of gravitational wave was emitted during the whole process and then integrate over them to calculate these coefficients a mu nu, b mu nu, and c mu nu. Sorry, a mu nu, b mu nu, and f mu nu. And in fact, again for a mu nu, this effect was known earlier. This is what people call nonlinear memory. This happens because gravity is self-interacting. But it turns out that there is a miraculous cancellation, and because of this, in the expression for b mu nu and f mu nu, the contribution from the massless final states can be expressed in terms of massive state momenta. And I'll explain in the next slide how this goes. So here is a identity, What this identity says that in the expression for b mu nu, we can just drop all massless particle and radiation contribution in the sum over final states and simply compensate by adding a term like this, where here pi is the total incoming momentum of all the objects and pf is the total outgoing momentum carried by only the massive objects, not the massless ones. So you see that this expression can be calculated knowing only the massive final state particles, and so you don't need to know what kind of gravitational wave was emitted during this process to evaluate this coefficient B mu nu. Okay. And there is a similar expression that exists for F mu nu, right? We just drop some of our all massless particles in the final state and then compensate this for this by adding this. Okay. And I should just add that these are not new formulae, but they just follow from manipulating the formula that I gave earlier. Okay. But at the same time, I should also add that at present there is a deeper understanding of why this happens. Right? It's just an observation based on examination of the formulae, that we can just drop the massless states in a final state and replace it by these additive terms like this. Right? And it will certainly be useful to get a better physical understanding of why this is possible. Again, this is a technical point. If the incoming and outgoing particles carry charge, then there are additional terms in this formula. So in the formula that I showed you, I implicitly assume that the incoming objects and the outgoing objects are chargeless. Right? If they do carry charge, then we have to add new terms in the formula, but they are known terms. Right? It's just the formula will get a little more complicated. Okay. And we began with explosion. Right? Explosion can be regarded as a special case of scattering. Okay. When the initial state just has one object. Right? So in this case, C and G will be 0, and the E mu nu will be given by this expression at large positive U. Right? For large negative U, there is no E mu nu, it's just 0. And a final point, again, this I have emphasized before. Okay. These results that I gave you, right, are statements in classical theory of gravity. However, it turns out that they are easier to understand as classical limits of some results in quantum theory of gravity. Okay. And these results are known as quantum soft graviton theorem. Okay. And as I told you earlier, that the tail terms that I showed were first predicted from quantum soft graviton theorem, and then a fully classical derivation was found. Okay. So what I am going to do next is to explain how what quantum soft graviton theorem is and how it helps getting this classical result. Right? I will not go into the details, but I will just give you the principle of how we use quantum soft graviton theorem to get this classical result. So in quantum theory of fields, the scattering amplitude A gives the probability amplitude for transition of one state to another. Right? And the relationship between the scattering amplitude and probability is that you just, A is a complex number, you just take the absolute value square of that complex number, and that is the transition probability. Okay. Now let's suppose that you have a scattering, right? Some initial state A consisting of a set of particles going to a final state, initial state P containing a set of particles going to a final state Q containing a set of particles. Okay. And let's denote the scattering amplitude by A. Okay. Now what soft graviton theorem achieves, okay, is that it gives the scattering amplitude of a new process. You consider a scattering amplitude where P goes to Q plus some low energy gravitons. Now what are gravitons? Gravitons are quanta of gravitational fields, just like photons are quanta of electromagnetic field. So gravitons basically play the same role as photons, as gravity plays, as photons in quantum theory of gravity. Okay. And just like the photons, gravitons are bosonic particles, right? And this is going to be important. So they are indistinguishable, right? And they are symmetric under exchange. Okay. So soft graviton theorem gives you the result for this process, P going to Q plus some low energy gravitons, in terms of the amplitude for the process P going to Q. Right? So it basically says that if you know the answer for some particular process, then if you want to include a few more gravitons in the final state, the result is easy. Right? You have a simple formula to relate the two. Okay, so now we are going to take the classical limit of this theorem. Right? So how do you take the classical limit? So first of all, to take the classical limit, you have to take the initial states P and Q to consist of very heavy objects, right? Because we need classical objects in the initial and the final state. So we take the initial states P and Q to consist of very massive particles, Okay. And now we compute the transition probability for P going to Q plus M low energy gravitons, where M is an arbitrary number. Okay. And it turns out that according to soft graviton theorem, this transition probability will take the form of A times B to the M over M factorial, where A and B are constants. Okay. You see what A is, if you set M equal to 0, that means consider transition probability for P going to Q, that's A. Okay, so A is a complicated object, right? You don't know how to calculate A in general, but fortunately you will not need the value of A. The effect of B essentially tells you how to add a certain number of low energy gravitons. For every low energy graviton that you add, you get a factor of B. So if you add M low energy gravitons, you get a factor of B to the M in the transition probability. Okay, here I have already squared the amplitude to get the probability. Okay. And then comes the crucial factor based on the Bose statistics. Okay. Because the final state gravitons are bosons, they are identical particles, we have to divide by the symmetry factor of M factorial. Because if we exchange two final state particles, right, it's not a new state, it's the same state, right? So you should overcount. So this is the expression for the transition probability for going from P going to Q plus M low energy gravitons. Okay. So as I already said, A depends on the details of the scattering process, but B is a universal quantity. It depends only on the initial and final momenta due to soft graviton theorem. Okay. Now this is the spirit in which quantum mechanics works. Quantum mechanics never tells you what the final state is, but it simply tells you how to calculate the probability for different final states, right? And that's what it is saying, how to calculate the probability for producing M gravitons. Okay. But now you see, if you take this expression and study how it depends on M, okay, you will find that it has a very sharp peak at a particular classical value of M, and that's M equal to B. Okay. So basically you take the logarithm of this, use Starling's formula, and then maximize with respect to M. Right? Now of course M is not a continuous variable, so once you maximize after regarding this as a continuous variable, you can pick the nearest integer. It doesn't really matter whether you go up or down, right? Because that's just a difference of number 1. Okay. But basically what happens is that the B become in the classical limit, B turns out to be a large number, and the expected value of M, which is equal to B, is also a large number. Right? And because the peak is short, this tells us what is the expected classical number of low energy gravitons that is produced during this process. Okay. And once you know what the classical number of low energy gravitons is, right, you can, there is a standard procedure by which you can convert this to what kind of H mu nu it will produce. Because H mu nu, the number of classical gravitons is related to the strength of H mu nu field. Right? There is a standard procedure that transcribes it. Okay. And that's what leads to the quoted result. The complicated formula that I showed you basically comes from applying the soft graviton theorem and taking its classical limit. How much time do I have? Total 10, okay. Okay, so let me say a few words about the direct classical derivation, right? I will not go into very much details. Okay. So in the direct classical derivation, the goal is that we want to find H mu nu or equivalently A mu nu generated during the collision process. Okay. And the trick is that we rewrite the Einstein's equation, which is very complicated, in this simple form, okay, where we write as box E mu nu as minus 8 pi g T mu nu. T mu is known as the energy momentum tensor. Okay. But this is in fact deceptively simple, because this all nonlinearities of Einstein's equation I have basically dumped into the right hand side, right? Anything that is nonlinear I have taken to the right hand side and written it in this form. Okay. So this is really a highly nonlinear partial differential equation, but written in this form. Okay. And it's complicated because of two reasons. First of all, as I said, T mu nu has nonlinear dependence on E mu nu, but it also has dependence on the trajectories of the various particles. Okay. And those trajectories themselves are dependent on E mu nu because they are controlled by what kind of gravitational field is present. Okay. And this, what the exact structure of T mu nu may not even be known if the interactions are not known. Okay. Nevertheless, we go ahead and formally solve this equation. Okay. We formally solve this by writing E mu nu as the integral of the retarded Green's function convoluted with T mu nu. Now it turns out that it's little simpler to work with Fourier transform variables. So we define E tilde mu nu, where you take the Fourier transform with respect to the first time variable, right? E tilde mu nu of omega and x. Okay. And then by using the property of the retarded Green's function, one finds that E tilde mu nu of omega and x have this expression like this, which involves now a full the Fourier transform of t in all 4 variables. Okay. And the momentum the 4 momentum that appears in the exponent essentially is controlled by omega, right? So its magnitude is 0 component is just omega, and its spatial components is omega times the direction vector x over mod x. Okay. Now what is the main point of doing this? Okay. Main point of doing this is that when you look for a behavior like E mu nu goes as 1 over u for large u, one can show by simple Fourier transform that this corresponds to, in the Fourier space, E tilde mu nu going as log omega for small omega, right? So this statement is equivalent to this statement. Similarly, E tilde mu nu going as log u over u square corresponds to E tilde mu nu going as omega log omega square. And the main point that I want to focus on for these 2 expressions is that these are non-analytic as a function of omega. Okay. Now what do you mean by non-analytic? Right? Non-analytic doesn't mean that it's divergent. The first one is divergent, log omega does diverge at omega equal to 0, but this one doesn't. Okay. But non-analytic means that if we take sufficiently large number of derivatives of this with respect to omega, then it will diverge. Right? You can see that the first derivative of this with respect to omega actually diverges at omega equal to 0. Right? And that's what we mean by non-analytic. And that's what is going to be used. Okay. So here is the formula again. Okay. So now the idea is that we have this integral over the 4-dimensional space-time. Again, nothing has, we have not really put in any input. T mu nu is a very complicated function because it depends on E, right? And it depends on the trajectories of the particles, which in turn depends on E, right? So it's still a complicated equation to solve. Okay. But now suppose we divide the integration region that we see here into 2 parts. One is we call the scattering region, right? Which is the range where the actual scattering phenomena is happening, where the particles have come in together, gone out together, all the nuclear interactions, non-linearity of gravity are happening in the scattering region. Okay. So you divide this integration region into the scattering region and the complementary region. Another point is, you see that however complicated the scattering region is, okay, integration over a finite volume, okay, can never produce divergences. Okay, and that's irrespective of how many derivatives you take with respect to omega. Okay, so let's take this expression here. Right, omega dependence is here, right, through this k, right, and k has this omega times this vector. Suppose you take the derivative with respect to omega, right? What will it do? It will bring down some factors of y. Right, you will get y square, y cube, right? However many derivatives you take, you get some polynomials in y. But if you take the integration region over y to be over a finite volume, then whatever power of y you bring down, that never is going to produce a divergence. Okay. So divergence is going to come from the region that is outside the scattering region, the region that extends to infinity. Okay. And this is what simplifies things. Okay. So the idea is that the behavior of E mu nu for large u is insensitive to the contribution for the finite region. Okay. So in this formula then we can restrict the y integral to the region outside S. Okay. In this region only long range forces are important, which includes gravity and electromagnetism. Right. So if the particles are uncharged, then electromagnetism is not relevant. Right. Only gravity is relevant. Okay. And also in this region E mu nu is small, and as a result T mu nu also simplifies. Right. This has an expansion in powers of E, which is reliable. And then the idea is that we solve these equations iteratively. Okay. And by solving this iteratively, we get the result that we quoted earlier. So this is the classical derivation of this soft graviton of this theorem. Okay. So now let me make some comments and then I'll end. Okay. So you see that we have a classical derivation now, right? Even though the result was derived from soft theorem, right? We do have a classical derivation. Okay. Okay. However, we shouldn't play down the role of quantum theory, because it is really the quantum theory that teaches us the right question for which we have simple answers. Okay. Imagine that you are trying to solve this problem as a purely classical problem. Right? In a purely classical setup, the way we will set up the problem is that you have some initial number of particles coming in. We give their initial data, right, momentum and any other information that we want. Then we follow it, we evolve it classically. Right? And as you evolve it classically, you also try to calculate what kind of gravitational waves are going to come out during this process. Okay? And this is a very complicated problem, because as I said, this problem can only be solved by taking into account the full nonlinearities of gravity. Okay? It's only in the quantum theory, right, then the kind of questions that we ask, right, is to specify the initial state and the final state, and we ask questions about that state. Right? The scattering amplitude is exactly that. We specify the initial and the final state, and we ask for the probability of that event to happen. Okay. So it's in this sense, is the quantum theory that tells us specifically, that teaches us to specify both the initial and the final state of matter, and then ask the question about radiation emitted during the process. Because in this sense, quantum theory really plays a role in giving us the right guidance as to what questions to ask. Okay, and this is my final slide, possible generalizations. Okay. It turns out that there is reason to believe that it's the two coefficients that I have showed you, right, in the initial state and the final state, the ABF coefficient in the final state and the B and G in the initial state. Right? Those are not the only universal coefficients. Okay? There is reason to believe that if we look at large U and look at the coefficient of U to the n minus 1, U to the minus n minus 1 log U to the n, okay, these coefficients may also have universal properties in the sense that they depend only on the momenta of the particles. Okay. This is just a guess, but we don't have a formula, right? So the question is, can you compute them? Okay. In this case, Hopf theorem is not useful anymore, because Hopf theorem doesn't quite work for n greater than 1. But direct classical derivation may be possible, and this is some work in progress. Okay. And the reason that you want to study this, okay, is something that I have already alluded to earlier, is that if we can calculate the coefficients of these terms, right, then those are the coefficients that we measure in experiment. Okay. And if we know these coefficients as a function of p, then the experimental knowledge of these coefficients can be used to turn the situation around and determine what kind of particles actually collided during this process. Okay. Because that's what we really want to study. That if we detect gravitational wave from a signal, gravitational wave signal, we want to know what process produced it. Right? And knowledge of these coefficients, okay, can in principle tell us what process produced the gravitational wave signal, because we will know exactly by reversing these relations as to what went in and what came out during this process. But this is still work in progress, so I'll stop here. Thank you.
Okay. Questions?
That was a very nice talk. It reminds me of soft theorems in QCD. And of course, Lowe's theorem, where if you throw a photon at a low energy, all you will see is the charge. Throw it at a larger energy, you'll see details like multiple moments and so forth. But what I found very intriguing was that h bar is equal to 0 in all your calculations here. And yet you can go to QFT and be inspired by that and get results for h mu nu.
Yeah.
But so, one question to you, my question to you is, in QCD and QED, the word identity is really what is responsible for the soft theorems. Is there a word identity that inspired you here?
Yeah, there is some kind of word identity. Right? We don't really directly use word identity for soft theorem, but certainly gauge invariance plays a role. Right? You use gauge invariance to derive the soft theorem, even in this case. right? The gauge invariance means general coordinate invariance of the scattering amplitudes. Yeah, and as you said, I mean, there is no h bar in the formula, but this calculation did involve h bar, right? It's just that h bars cancel at the end. Because you see, when you convert the number of massless particles to what the gravitational wave form, right? That has information about the h bar,
Yes, of course.
right? And this calculation also has information about h bar. At the end, the h bars cancelled, right? And we got some nice classical formula.
The essential singularity in omega, is that really coming because the gravitational waves have very little energy and your detector cannot detect those very low energy waves?
Yeah, so it is related to infrared issues that, as you said, that if you have very low energy waves, it cannot detect, but this is not directly related to that, right? Because that corresponds to having an infrared cutoff. That if we place a detector at, say, distance r from the source, then there is a natural infrared cutoff that a detector has, which is 1 over r, right? It cannot measure wavelengths that is longer than 1 over r. So that gives a natural cutoff, but this omega that is relevant is larger than that, right? So it's not limited by the infrared cutoff that the detector has.
Okay, thank you.
Professor Shen,
Yes.
what are the differences between the soft wave theory and classical gravitational theory of Newton?
Well, see, soft graviton theorem is a theorem in quantum theory of gravity, right? So it's not a theory by itself, it's a consequence of quantum theory of gravity. And what this is saying is that somehow the classical results in gravity are easier to understand as limits of quantum results in gravity, right? So it's not a new theory, right? It's just a new way of using quantum theory of gravity to get classical results.
Okay, what are the detectors that you have done the theoretical work? You mentioned the LIGO as a detector, yeah?
Yes. Yeah. So LIGO, well, it turns out, unfortunately, cannot detect these kind of terms, because what happens in LIGO is that once the gravitational wave passes, there is a restoring force which brings the detector back to the original state. So the late time behavior, the LIGO cannot capture. But there are these space-based designs, LISA, right, which will be detectors in space, and they will certainly be sensitive to these kinds of effects, because there is no restoring force that will bring the detectors back. So once the gravitational wave passes, it will see everything, right, till the very end of time.
Okay, thank you.
Okay. Yeah, thank you for the very nice talk. So when you say quantum theory of gravity, do you mean taking the Einstein-Hilbert action and quantizing, or like the canonical way of quantizing gravity?
Yeah, it turns out that it doesn't really matter, right? I mean, if you take the Einstein-Hilbert theory and quantize it, you have these various ultraviolet problems, right? There are ultraviolet divergences. So you can think of this as a limit of some string theory where the ultraviolet problems are not there. But it turns out that these low energy theorems, right? For these low energy theorems, it doesn't matter really how you complete in the high energy, right? The low energy physics is universal.
And just to ask, so as you mentioned, it might come from a low energy limit of string theory. So what about the higher order corrections to the Riemann tensor, like alpha prime corrections?
Those don't affect the soft theorem. Yeah, so those have been studied, right? So that's the sense in which this is completely universal. You don't need Einstein's theory, right? If you have Einstein's theory plus these higher derivative corrections, they don't affect the soft theorems at the order that we are studying here.
Okay.
Right? I mean, if you go to higher order, right, they may start affecting, but not at this order.
Yeah, I asked this because there was this paper earlier this year by Gary Horowitz and friends. So they were studying Kerr-Neumann black holes, and they got this like alpha prime corrections were affecting the singularity and setup in their paper.
Yeah.
So yeah, if you're taking the Einstein-Hilbert term, and there might be cases when the alpha prime corrections are not negligible.
Yeah, that is certainly true, but this doesn't happen in the infrared, the kind of issues that you are studying, okay? Because this certainly has been studied, that what is the effect of these higher derivative terms on the soft theorem, and one can show that it doesn't affect the results to this order. So this is, it is in this sense that it is completely universal, right? You don't really need to assume that it's Einstein's theory of gravity. As long as you have general coordinate invariance, that's good enough for these results.
Okay, thanks.
Okay, was there another question?
Professor Ghosh.
Okay, yeah.
Oh, it was an excellent talk, but I'm a little foxed by one statement, if you could clarify,
Okay.
which is you talked about the classical number of gravitons. Now, gravitons are essentially quantum.
Yes.
So what does that mean, actually?
Yeah. So what I mean by the classical number of gravitons is this, that if you take this expression, right, this gives you the probability of emitting m gravitons in this process. And by classical number of gravitons, I meant the value of m for which this quantity is maximized. Okay. Because it's a distribution and it peaks around some value of m and the peak is sharp. Okay. So when you want to go to the classical limit, that's what you identify as the classical number of gravitons that are coming out. That it's in the sense of probability, right? Probability distribution. That even though the number of gravitons varies from process to process, right? If you repeat the experiment, you will get different number of gravitons. But most of the experiments will produce graviton in a very narrow range. The number of gravitons in a very narrow range. And that is what I am identifying as the classical physics.
Clarification.
Yes.
We still are waiting for the final quantum theory of gravity, right?
Yes.
So are you saying that no matter what that is, these soft theorems will hold in any way?
Exactly. Yeah.
Okay.
Yeah. Because the point is, this is based on just general coordinate invariance. Right? So as long as you don't break general coordinate invariance, these soft theorems will hold anyway.
Okay, I think we should move to the next talks. Let's thank Ashok for a really fantastic talk. Okay, so the next talk is by Professor Saurav Roy. He'll be talking about mixing of the photon with axion and axion-like particles.
Okay, first of all, I'd like to express my deepest gratitude to the organizers and in particular Professor Kamrul Hassan for giving me this opportunity and inviting me to speak at the centennial celebration of Bose-Einstein statistics. It's a great honor and a privilege for me. So today I'll be discussing about a spin zero boson called axions and more generally axion-like particles, which are ubiquitous in many theories of physics beyond the standard model, and its interaction with another boson, spin 1 photon. So I'll discuss their interactions and how to search for them briefly, and what are the consequences of these interactions. So let me go ahead. So neutral ultralight spin zero bosons, that is the scalar or pseudoscalar particles, Cp even or Cp odd, can have gauge invariant couplings with photons. As written there in here. So if the interaction with the scalar is given by f mu nu, phi s is the scalar, neutral scalar, and with the pseudoscalar it is given f mu nu tilde, the dual. So f mu nu is the field strength, electromagnetic field strength tensor, and f tilde mu nu is its dual, and lambda s or lambda p, they are some effective scale of mass dimension. So these are the gauge invariant interactions that scalar pseudoscalar particles, bosons, spin zero bosons can have with photon. We have a few known examples I already mentioned. Light scalar particle, pseudoscalar particle is axion, or there are other axion-like particles. They are pseudoscalar particle, CP odd. Axion is the pseudo-Goldstone boson of the so-called Peccei-Quinn symmetry, which, as I will discuss briefly, solves the strong CP problem of QCD. And the mass of the axion is expected in the range of the order of a few milli-electron volt QCD, which is coming from QCD. Of course, as we will discuss, the axion-like particles has a large range of particles have a large range of masses that we consider. And another spin zero boson which interacts with photon, we know very well, Higgs boson, which is a scalar particle, and it is necessary to provide all the masses in the standard model. And the mass experimentally measured to be of the order of 125 GeV or so. And this coupling of this Higgs boson with two photon, H gamma gamma, it is generated at one loop. So these are the examples that we know. Now, since we will be discussing about the axions, let me first briefly discuss the strong CP problem of QCD. So, considering the effect of the chiral anomaly of the U1 axial symmetry of QCD, an extra term is added to the QCD Lagrangian. So, you have LQCD plus this term, which is G mu nu tilde G mu nu. G mu nu is the gluonic field strength tensor, and G is the strong coupling, small g. Okay, and this theta term, theta G mu nu tilde, this is the CP violating term. Okay. Now, once we include the electroweak interactions, the effective Lagrangian of the standard model is given by this theta tilde, G mu nu tilde, where theta tilde is now theta plus contributions coming from the quark mass matrices, argument of the determinant of mu md, where mu and md are the up type and the down type quark mass matrices. Now, as I mentioned, this presence of theta bar implies violation of the CP invariance in QCD, which has never been observed. Because if such a term exists, then it will contribute to the electric dipole moment of neutron, which has a very strong experimental bound, dn, which is less than 10 to the minus 25 ECM or so. Now, if you have a theta bar term that I wrote in the previous slide, then this the contribution to the electric dipole moment of neutron comes out to be 10 to the minus 16 theta bar ECM, and which immediately tells from the bound that I have shown here that theta bar must be smaller than 10 to the minus 9. Okay. Whereas the natural order is of theta bar is order 1. So that means we require extreme fine tuning of theta to the value of argument of determinant mu by md, as you can see the theta bar term here. And this question of the smallness of theta bar, this fine tuning problem, is known as the strong CP problem of QCD. Now, an elegant answer to this strong CP problem, solution to the strong CP problem, was proposed by Peccei and Quinn. Okay. So, they propose an extension of the standard model of elementary particles with an additional spontaneously broken global chiral U1, which is called the U1 Peccei-Quinn symmetry, which is broken spontaneously at the Peccei-Quinn scale Fa. And the corresponding, as the symmetry is global symmetry is broken, we have a corresponding pseudo-Nambu-Goldstone boson, and that is the axion, which I mentioned previously. Now, this axion also couples to gluons such that the chiral anomaly in the U1 Peccei-Quinn current is reproduced. So, the interaction of the axion with the gluons comes like this: Fa by n. N is the color anomaly coefficient. GSS square by 32 pi square G mu nu tilde. Okay. So, this additional interaction Lagrangian is introduced because of the Peccei-Quinn symmetry here. Now, because of the presence of this interaction with of the gluons with the action and this theta bar term, this provide action field with an effective potential V effective. Okay. Non-perturbative contributions. Now, the coefficient of the CP violating GG tilde term becomes dynamical, okay? Because this will vanish when, because of this potential, if you minimize it, it vanishes for the value of the action field is equal to minus theta bar FA by N, at which we have this minimum of this V effective, okay? So it becomes dynamical and easily solves the strong CP problem of QCP. So this is the way action is introduced in the theory. So it's a pseudo-Nambu-Goldson boson. Now action receives a mass from its interactions with gluons, which essentially induces transitions to QQ bar, okay? Because it has interactions with gluons, it induces transitions to the QQ bar system. And that means it mixes with the neutral pions. So A and pi 0 neutral pion mix with each other, and because of this mixing, actions pick up a small mass. Okay, and that is given by this expression that I have written here. F pi is the pion decay constant, Fa is the coefficient that I have shown earlier. Okay. M pi is the mass of the pion, and Mu, Md are the masses of upward and downward. You can rewrite this mass of the action in a more convenient form by defining Z equal to Mu by Md. So as I wanted to emphasize, actions gain a small mass because of its mixing with the neutral pion. Now, original Pechiquin proposal assumed that Fa, this coefficient of this action GG tilde gluon-gluon interaction, to be at the weak scale, electroweak scale. Now, because of various searches for actions, astrophysical observations, and cosmological arguments, tell us that Fa should be much larger, about 10 to the 9 GeV or so. Okay. So that means since 1 by Fa is the coupling of the action to gluons, the action has a very weak coupling because it is suppressed by 1 over some 10 to the 9 or so. Now, you can see that action mass is inversely proportional to Fa. So since Fa is very large, this means action mass must be very small. So action mass is something like 0.01 electron volt or so. So because of this very large Fa, 1 by Fa is the coupling, action is also an extremely weakly interacting particle. Now there are as I said, that original proposal was to assume Fa to be at the weak scale, but this bound is there, so weak scale Fa is ruled out. Now there are other action models which try to introduce this kind of interactions of actions with gluons and give rise to action masses. So action interactions are model dependent, and the two most popular classes of phenomenologically viable invisible, so-called invisible action models are the so-called hadronic or KS-VZ model, Kim, Schiffman, Weinstein, Zakharov model, KS-VZ, or the DFSZ model, which is Dine, Fissler, Srednitsky, and Zitnitsky model. Okay. So for the KS-VZ type, at least one additional heavy quark is introduced, which couples directly to the action. All other fields do not carry any Pechiquin charge. Pechiquin is the U1 Pechiquin that I mentioned. Okay. Actions interacts with ordinary matter, that means the standard model particles, through the anomaly terms from loop of this new heavy quark through photon and then to other standard model particles. Now integrating out heavy quark loops, one obtains the effective dimension 5 coupling of actions to gluons that I have shown already. And as I mentioned, coupling of the action to standard model matter fields are suppressed by additional loop factors. Okay. So first coupling with the gluon and then. In the DFSZ scheme, no additional heavy quarks are introduced. Standard model matter fields are, and the two Higgs doublets carry appropriate Pechiquin charges. And at low energies, the action-gluon interaction arises. So these are the two most popular classes of action models that one discusses. And how, so our theme of the talk was to present the action couplings to photons and its physics. So how action couplings to photons arise? Mixing with pi naught generates coupling of the action to photons. Okay. Because pi naught couples to 2 gamma, so action mixes with pions because of its interactions with the gluons. So that means it mixes with pion, pi naught, and pi to 2 gamma. So that's the way interactions of photons with action is generated. So this interaction is written conveniently as Ga gamma gamma by 4, A F mu nu tilde, and I told you in the beginning that F mu nu is the electromagnetic field strength. And Ga gamma gamma coupling, that comes out to be this in terms of the mass of the action and quark masses and this EM anomaly coefficient and the color anomaly coefficient E by N. So if you take this coupling and this interaction of action to 2 photon, obviously, and since action has a mass, you know that action can decay to 2 photons, A to gamma gamma. Okay. And this decay is easy to calculate, it's a 2-body decay, and which comes out to be 64 pi by Ga gamma gamma square Ma cube. So goes as coupling square and inversely coupling square and cube of the mass of the action. And if you plug in the values of all the other parameters, you will see that the decay lifetime comes out to be 10 to the 40 seconds or so. So it's huge, it's a very large decay lifetime, which means that almost action is almost stable particle on cosmic time scale, okay? Because age of the universe is 10 to the 17 seconds, we get huge lifetime. So that means it can play the role of dark matter of the universe because it's stable, almost stable in the cosmic time scale. Now, what are the effects of this spin zero, which is action or in general action-like particles, to 2 photons on the photon propagation? Okay. So if you consider one of the gamma as the background magnetic field B, okay, so that gives a mixing term in the photon spin zero system. So the photon spin zero conversion is possible in the presence of an external electromagnetic field, which goes by the name of Primakov effect, and which is shown here in this diagram. So you see that in the presence of electromagnetic field E or B, photon mixes with the action, and photon action conversion is possible. And obviously it could generate photon spin zero oscillations for photons propagating in magnetic field. And that is what we will try to explore further in this talk. So because of this photon coupling with the action, there are certain astrophysical constants that come up. So action can be produced in hot and dense astrophysical environments like ordinary stars, white dwarfs, supernova, etc. And the action luminosity LA depends on this coupling 1 over Fa. So the relevant production process, astrophysical models of the source, these also affect the luminosity. And a sizable LA is associated with additional energy transport out of the source. Okay. So stars will lose their energy through these actions because they are very weakly interacting. They will be produced inside the star because of this Primakov process from the photons inside the thermal plasma. Produce actions, action come out of the star, they will take additional energy, and so that will affect the sources that I mentioned. Okay. So this will affect the behavior of the source strongly, and astrophysical studies of stars, white dwarfs, supernova, etc. can be used to derive constants on this coupling Fa or the mass of the action. So let me repeat it once again. In stars, including our sun, actions can be produced through the Primakov effect, which is essentially that in the electromagnetic field of a charged particle, photons can get converted into actions through this process. Okay. Axionic, as you can see, this coupling is Ga gamma gamma. So axionic energy drain luminosity is proportional to Ga gamma gamma square, and leads to an enhanced consumption of nuclear fuel within the star, because there is additional energy loss from the star because of this coupling. So this shortens the lifetime of a star. And the globular cluster stars, which are bound systems of a homogeneous population of low mass stars, people have studied, and they allow for tests of this kind of stellar evolution theory, and in turn it gives a bound on the axion photon coupling, which is about less than 10 to the minus 10 GeV inverse or so. As I mentioned, photon spin zero photon action conversion can also lead to photon action oscillation phenomena. Okay. So if you write down this F mu nu tilde axial interaction in terms of electric field and the magnetic field, the interaction looks like A E dot B Ga gamma gamma. Okay. So you already noticed that. So that induces a mixing between photon and the action in the presence of a background magnetic field. Okay. Now, if we consider the photon polarization with electric field parallel to the external B, because the interaction is E dot B, you can imagine, you can easily see that this photon polarization, which I denote by this electric field E, parallel to the external magnetic field only mixes with the action because of this E dot B coupling. So that gives an equation involving the parallel component of the electric field and the photon polarization parallel to the magnetic field and the axion. This is a 2 by 2 mixing problem. Okay, so that's a 2 by 2 mixing matrix that is there. Okay, so you solve this and find out the solutions, and you can calculate the probability of transition from axion to photon, which is given by this expression sin square 2 theta sin square half kx. And this mixing angle depends on the magnetic field B, this coupling Ga gamma gamma, it will be Ga gamma gamma, and the energy of the photon and the mass of the action. Okay. Now, this action photon oscillation was proposed as one of the possible explanation of the dimming of the distant type 1a supernova that was observed. Okay. And people considered about intergalactic magnetic field, which is not constant, and total photon oscillation probability was averaged over many magnetic domains. So that was a proposal long time back, considering this photon action oscillation in the context of this dimming of type 1a supernova. Now, there are also axion searches coming from the sun, which are solar axion searches. So, you know that the most important and strongest astrophysical sources for axions is the core of the sun, and where axions are produced again through Primakov effect and other Bremsstrahlung and inverse Compton scattering and all these processes. So, axions could be produced because of the presence of magnetic and electric field in the plasma of the core of the sun via this two photon coupling. And after production, they freely stream out of the sun. So one can estimate the differential solar axion flux on Earth, which is given by this expression. And one can also check that the spectral energy distribution of the axion peaks at about 3 keV. So this is essentially the idea of searching for axions. So the most sensitive part of the mass window is between 10 to the minus 5 eV and 1 eV. This system is called the axion helescope, okay, the magnetic solar telescope. So axions are produced in the sun through this two photon coupling. It travels all the way to Earth, and then there is a detector where you have a magnetic field. So then these axion get converted into photons, converted back into photons, and because it's a keV range, 3 keV is the peak, it's X-ray, and there is an X-ray detector where you detect this photon, and from there you can give bounds if it is not seen insufficient amount, you can give bounds on the axion mass and coupling. Okay. Now, now this quantity, this momentum transfer Q depends on the mass and the energy of the mass of the axion, energy of the photon, and there is a range of sensitivity that I have shown here in the mass of the axion. Now, these are the astrophysical context we discussed, the axion to photon coupling. Now, axions can be searched for in laser experiments, okay, in laboratory setup. Okay, what is this? So purely laboratory-based experimental search for ultralight pseudoscalar particles, scalar particle is possible. So it is possible because it's a laboratory setup. It's possible to make accurate measurements on the modification of the polarization state of a light beam. I explain what it is. Okay. So what happens is that a laser light is reflected back and forth n times between two mirrors. Okay, in a constant magnetic field orthogonal to the beam direction, so that total path length is increased, traveled by the laser beam in the magnetic field. So AL is about a few kilometers. Now, to start with, the laser beam is linearly polarized. So the electric field, which corresponds to the polarization vector of the electromagnetic wave. Okay, so laser beam is linearly polarized to start with, and after traversing this distance L of the order of a few kilometers, it is possible to measure small ellipticity in the polarization and change in the rotation of the plane of polarization of this linearly polarized light. So these can be measured, and this way one can study this axion two-photon coupling. So let me just explain what exactly I was discussing, how rotation and ellipticity is generated. So B external is the external magnetic field, and we have this E vector, which is corresponds to the polarization of the electromagnetic wave, the photon. And we have two components. One is E parallel and E perpendicular, parallel to the magnetic field and perpendicular to the magnetic field. Now, because of this axion photon conversion in the external magnetic field, the parallel component mixes, so it is reduced, and you can see the resultant is of course rotated by some amount epsilon in the top part of the figure that I have shown. And not only that, you see, because of the same axion photon two photon coupling in the presence of the magnetic field, you see there is this E parallel which is retarded. Okay, so there is essentially, in other words, it induces some kind of a phase difference between the E parallel and the E perpendicular. And because of this phase difference, the linearly polarized light becomes an elliptically polarized light, as shown here. So this ellipticity can also be measured. So from these measurements, one can, so this means ellipticity means that E parallel and E perpendicular, you have two different refractive indices for these. Which is called the birefringence of the vacuum. Okay. So this is birefringence, and rotation is called dichroism. So birefringence and linear dichroism of the vacuum are characterized by this quantity epsilon and theta, or psi. I wrote psi in the previous slide, and which depends on the mass of the axion and the magnetic field, total path length, and this inverse coupling M, which is defined as 1 over G gamma. One can measure this, try to measure this quantity in experiment and laser experiments, and then put bounds on this. If nothing is observed, put bounds on this coupling and mass of the axion. There is another type of experiment where one look for axions and its coupling with two photons. It's called light shining through wall experiment. So what happens is that after a laser beam passes through a magnetic field, as you can see in this diagram, so laser beam is passing through the magnetic field, so there is a magnetic field. So an axion component is generated along with a photon component. Axion is weakly interacting particles, so it penetrates the wall. Photon is absorbed, there is a thick wall there. Photon is absorbed, the axion penetrates the wall, go to another magnetic field. There, because of this two photon coupling, it is again reconverted into photon, and there is a detector which detects this photon. Okay. So because there is a wall and you see the photon behind the wall, it is called a light shining through wall experiment. Okay. So, however, this is a small effect, very small effect, because you introduce two the square of the axion photon oscillation probability, which itself is a small number. So after all these things, briefly I discussed laboratory setup, how you constrain the this thing, the coupling of axions with two photons, as well as from astrophysical considerations. You see that these are in the plane of the axion mass and the coupling. So this is basically the constraints that we obtain from action mass and in the action mass and coupling plane. This line here, this yellow line, this is the QCD action prediction for action mass and coupling. And this cast, which is written, that's the CERN axion solar telescope. I showed you how to look for actions coming from the CERN. So this cast experiment look for action this way, CERN axion solar telescope, and they give bound on this in the mass coupling plane of the axions, as well as coupling constants from the globular clusters are there. And there are other, the top part of the constant plane, this plane is constrained by laser experiment that I was discussing earlier. There are other experiments which I could not discuss. Also constants come from the collider experiments. Okay. So, so this is, as we can see that this action to photon coupling, it has very important implications in the context of astrophysics and also in the context of laboratory experiments to study this. Also, one can look at this in the context of cosmology, which I didn't discuss. So it has implications in the context of dark matter. As I mentioned, it has a long lifetime, so it can be a candidate for dark matter. So this is what I wanted to discuss with you and show you that how important this action physics is and its coupling with two photons. So let me come to my conclusion. So as I mentioned, actions appear as a solution to the strong CP problem of QCD, and coupling of actions with two photons is possible, and it has several implications. And constants one can derive on the action photon mixing from various astrophysical and cosmological and laboratory observations. Actions or ALPs, which I did not discuss, can act also as cold dark matter. So it tells us that action searches are very, very important. So with that, I'd like to stop my presentation. Thank you.
Thanks. Questions?
Yes.
So thank you for the very nice talk. So you mentioned axions acting as dark matter candidates. So is there enough tuning freedom left in QCD axions to drive things like inflation, even though the scale of, let's say, the inflation and if inflation happened?
So I discussed about axion as well as axion-like particles.
Okay.
So axion-like particles, they have more freedom. So certainly they can act as a candidate for cold dark matter.
No, I wanted to know specifically about the QCD axion.
Yes, QCD axions, I think you can still use it as a candidate for cold dark matter.
So it's not ruled out by experiments?
It's not
okay.
ruled out by experiments. Yes.
Thanks.
Very comprehensive survey of axion searches. But I'm surprised you didn't mention neutron stars, pulsars, which are a very intense source of...
Absolutely important.
Yeah.
So I restricted myself to this, absolutely, because they have strong magnetic field, as you are mentioning. So neutron stars. So there are studies involving neutron stars and pulsars, and that also put strong constraints on action to photon coupling, and that have been studied. Those things have been studied.
My second question is, the universe should be full of axions because there were so many photons in the beginning, so we should see them all over. But if they are there as dark matter, well, that dark matter will be converting into photons and then it won't be dark.
No, see, as I told you, axion decays to two photon, that is possible because of this coupling, but I mentioned that lifetime is 10 to the 40 seconds. Okay, so decay is, lifetime is very long, so action is a stable particle. Okay, and regarding the conversion, of course, you have to remember that conversion, if you are thinking about intergalactic magnetic field, the magnetic field strength is 10 to the minus 9 Gauss. So probability of conversion is not that big. Okay, so it's not that all the photons will be converted into axions and you have full of axions. Okay, so that's the idea. So axion is a stable particle, and because intergalactic magnetic field is very, very weak, so conversion probability is very small.
And the polarization that you talked about, that's in flight, and it's because of the virtual conversion from axion to photons and back. Is that the reason?
That is a laboratory setup.
Yeah.
So that is essentially you have a laser beam in a laboratory. You are sending it through the magnetic field, which is transverse, and then it converts into axion, and then so there are two types of
Virtually.
Yes, virtually
Yeah.
it converts into axion, and then there are two possibilities. One is the measurement of the electricity because of this phase difference. Another is the rotation of the plane of polarization.
Thank you.
Professor Saurabh Rai, thank you for a nice talk. Yeah, my question is, how could you measure the lifetime of the axion? This
Yes.
is of the order of 10 to the 40 seconds. It's quite at a large time, yeah?
That's right, yes. So
How could you measure that?
Sorry?
How could you measure that lifetime of the?
No, you cannot directly measure it, obviously. This is a calculation, this is an estimate
Yeah.
for the lifetime of the axion. Just to point out that it can be a source for dark matter. Because lifetime could be, because natural scale of this lifetime is 10 to the 40 seconds. So it could be a candidate for
You said it's almost stable.
It's almost stable. Yes.
Why do you call it almost stable?
Because
Its lifetime is so large.
no, still one or two actions can decay. Okay?
Yeah.
Because it's a probabilistic.
It's a probabilistic,
phenomenon. So
yeah.
one or two actions can still decay.
Yeah, okay. It's good. Thank you.
Thank you.
Okay, last question.
Thank you, Chair. I just had a small question. It's just something bugging me because I've been trying to work on this kind of things for a while, but not in the astrophysics direction. So this is something you would observe whenever you add a theta term to your thing. So this I think I'm going to refer to this Witten effect. So the momenta of the electromagnetic field changes is no more E, but it's a combination of E plus theta B. So your axion effectively acts like if you had freezes to a value. I missed one of your slides while you actually were discussing this Pechequin thing. There is a cos, right, there's a potential that's given which is in the form of cosine. Was it in here or not? I mean, there is also a paper by Wilczek, if I remember this right. Right. So there's also a cosine that pops up.
Potential cosine.
So if you have multiple vacua, you can actually have objects which actually takes different values, whose frozen value you would actually equate with theta, to the theta parameter. So if that is the case, then the momentum changes because pi is no more E. It is E plus theta B. And if you want to write down the Hamiltonian, then you immediately get it's not pi squared plus B squared, but there's also another term which actually shifts the B. So naively, when you think of it in analogy with harmonic oscillators, that would shift the frequency pattern that you would be, observing with the photon in this background. So wouldn't it affect, let's say, in the microwave background radiation if you look at this thing?
CMB will be affected by this.
Right. So given this, I mean, has there been any experimental searches?
I have to check. Okay, but this is certainly possible. CMB will be affected.
We can talk about it after this session. I mean, if you wish. I would rather yield and give room for other questions. Thank you.
Okay, so I think we should move to the next talk. So let's thank Professor Roy for a very nice talk. Okay, so the last talk of the session is Symmetry and Solution Generation in General Relativity from Lie Groups to Black Holes by Professor Muhammad Akbar.
Hello, everyone. It's an honor to be here, and thank you all for inviting me over, especially Professor Kamrul Hassan, who took extra care that I am here, and other speakers are here. And it is an honor to be part of this conference for two reasons. Number one, I was a student at DU, and one of my heroes was, of course, S.N. Bose. as well as Stephen Hawking, Richard Feynman, as you know. But S.N. Bose had a very profound effect on us because, we can relate more to him, his stories. And of course, everyone knows, the profound contribution he has made. Unfortunately, my talk is not going to be on bosons, at least directly, but indirectly, certainly, because I will be talking about gravity. If you quantize gravity, you get graviton, which is a boson, on which Professor, Ashok Sen has spoken a little bit earlier. So, but there would be a general theme here, and Professor Hassan has urged me to keep it, understandable for the students here. So I added a lot of background to my original talk over the last 2 days. So bear with me and be prepared to, follow. Even if you don't follow, try to follow the cloud, as I put it. You will see, you will get to the bigger picture at least, with some smaller details as well. Okay, the title of the talk is already here, so there is nothing much to add there. And so the first theme of this, the general theme, the general backdrop, is that geometry and physics have a very shared, and like a fruitful interaction between them over the course of time. So let's briefly see what we know about geometry and how physics came alongside. So Euclidean geometry, which was first studied before Christ, and this is something that we still study today exactly the same way, because the first field of math which entertained what we today call proof. And then there is a big, fast forwarding, René Descartes introduced Euclidean, married geometry and, with algebra by introducing his X and Y coordinate system. And this facilitated studying functions on y-axis and x-axis being the basic thing you learn in undergrad. And then this facilitated the discovery of calculus, and eventually which led to the field of analysis. And analysis is the field that we require today to describe geometry locally. So, and later, Gauss showed that, there are more geometries than Euclidean geometry, and later Gauss showed that the Gaussian is an intrinsic property of a surface, and it is related to its topology. This is the first connection, again, all done through, what you learned from calculus, in a sense. And then, within 3 decades, Riemann developed Riemannian geometry, which describes any space of any dimension. And he showed Gauss was primarily concerned with 2 dimensions, surfaces, basically. So on the physics side, everyone is familiar in this room about F equal to ma and universal law of gravitation. I always wondered why the word universal, and then as a student, then somebody said it is because one of my teachers said that, of course, apple used to fall. But this showed that apple fall is related to, the motion of planets, same principle. So this Newtonian mechanics has been extremely successful in explaining everything that is listed over there, and still good today for daily life applications. Okay, now taking a geometric look of what you know about Newtonian physics. We know from everyday experience that physics law should be unchanged from point to point. If it changes from point to point, it is not a law. And if it changes from morning to evening, it is not a law. Okay, so, and it should be the same in any direction from our experience, and should remain the same, as I said, in any, for at least reasonably in a local time span. Maybe in the beginning of the universe and later time of the universe, we might be having different physical laws, but our experience tells us that the laws we should be calling laws within our time frame at least should have these properties in the Newtonian picture. So what Newton discovered is basically that we have a stage called Euclidean 3 space, E3, and time is a parameter. So Newton's paradigm is E3 cross R. And as you have seen this, little expression there in your doing calculus, that E3, you probably have done a lot of calculation using E2. E3 is locally described by this following metric, ds squared, which is the length, gives you the square root of that gives you the length, infinitesimal length, is equal to dx squared plus dy squared dz squared when you are using Cartesian coordinates. Of course, you can rewrite it in polar coordinates, but that wouldn't change ds squared itself. So you'll get the same length irrespective of which coordinate system you're using. Okay, so this would allow you, this metric allows you to do all computations, that we are familiar with. For example, finding the length curvature of a path of a bee flying from a certain time t1 to a certain time t2, or from a certain point to another certain point in Euclidean space. So the interesting part of this, which is like a metric of E3, is that this metric is invariant, meaning it doesn't change. If I rotate it, meaning ds squared wouldn't change, and and translate it. So this property that this metric doesn't change, or formally we say invariant, under this rotation and translation reflects what you call in the group theoretical language is that the group of E3, meaning Euclidean 3 space, which ellipse is invariant, is the Euclidean group. It's like a tautological to be using the same word. Anyway, Newton's law of motion is also invariant under this, Galilean transformation, which is again should be taken into account when we are talking about Newton's law of motion, not just the stage, not just E3. I think the charge is gone. Can somebody get me a correct charger? Yeah. So, together, Newton's law of motion is invariant under what is called the Galilean group. I would soon tell you about the group thing in a second. So after Newton, the biggest change in history of science was probably Maxwell's equation of electromagnetism, and this is the famous 4 equations, which is commonly written in. You can write it in more compact form, to scare your friends, And again, funny thing, it is not invariant under Galilean group. It is invariant under a different group, meaning the set of changes, like set of transformation, which would leave this equation in this form is called Lorentz group. Yeah, and this includes the rotation that we talked about, the Euclidean rotation, as well as something new called boost. Boost are the things that mixes time and space part. So in other words, the bottom thing, as Einstein realized, many people knew about this Lorentz transformation, but then it was Einstein who realized, this is how to, put it nicely. Of course, Einstein and Minkowski at the time, this whole thing and the transformation properties that leave these 4 equations invariant suggest that we live in a space-time rather than a space and time, where time is a parameter no longer. Space, time is taking in the same footing as space, but the only little difference is this -1. So if you write it in the matrix form, you will get a matrix -1 plus 1 plus 1 plus 1 diagonal, as Professor Sen was mentioning in his talk, and he called it eta mu nu. I would call it g mu nu for later purposes to be consistent with later. Okay, so this ds squared, the line element, again gives differential distance. It could be, unlike the Euclidean case, it could be positive, negative, or 0. So this square is still used even when it is negative. But it is understood that's a negative quantity. So after long struggle, Einstein realized how to combine his special theory of relativity, which was incompatible with theory of gravitation. So how to combine them, and that thing came through the general theory of his thought, was succinctly put in the general theory of relativity, which uses the Riemannian geometry that I mentioned earlier, developed by Riemann. So Einstein saw that and he realized that these are the key things. So you have to use tensors and Riemannian geometry language to express his thoughts. Okay, so you see, Einstein was very much, guided by Riemannian geometry at that time. And note that, those who are here, like undergrads and graduate students, that at around the same time general relativity came, quantum mechanics developed, but the paradigm is still E3 cross R, Schrodinger equation. So I have been using the word group a lot. Just to quickly tell you, there is nothing scary about it. Group is a set, with a binary operation, which you'd call it group operation, star, for example. And it should follow a set with a certain set of number of elements, which could be infinite, countably or uncountably infinite. But it has the following properties, that combination of any two elements would be within that group, and then associated property, you are familiar with this perhaps, like A combined with B, and then combined with C, is the same as combining the other, meaning combining the way you want it as long as you have the same order. And there would exist an identity element E, which combined with any group element will give you back that group element. And there has to be an inverse for every element. So identity its own inverse as well. So take simplest example is R, real number line with addition. Any addition of any two, addition being the group operation, addition of any two numbers is another number on that real number line, meaning within that set, that's closure. And addition of any three numbers, well, like first add any two number and the third number, it has associated property very easily. And addition with 0, 0 is the identity element. And 1 over that any number is the inverse of that number. Another one would be this real number line with 0 taken out under multiplication, and then positive part of real number line under multiplication. And this can be, of course, mapped to that one, meaning these two groups are isomorphic. Anyway, we don't need that so much. So most important part is Lie group. Lie group is a certain type of group that depends on continuous parameters, hence, and whose elements vary smoothly. Okay, there is a detail, those who go into a little bit of mathematical definition, you would see this smoothly has a very mathematical meaning, but intuitive understanding is good enough for now. So technically, it is also a smooth manifold, and where group operations are smooth functions. So simplest example of a Lie group is the group of rotations. Say you are familiar with this. If I rotate like around x-axis, z-axis, z-axis here, this is like x, y, and z would be mapped into x prime, y prime, z prime. If I rotate each and every point in this space would be turning around, except those on the z-axis. So this thing, this matrix, depends on this parameter theta smoothly, and theta takes on a continuous value. So this, collectively, all these different values form a group. And this is only about rotation about z-axis. You can similarly think of rotation over x and y-axis as well. The funny thing is that, these rotations, when you take them in totality, all three rotations about three different axes, they do not what is called commute. Meaning if I rotate, you can just try it now, take your phone, rotate it around z-axis by 90 degree, and then rotate it around y-axis, another 90 degree, and do the same thing the other around, you would see that position of the phone would be different. So meaning we can have Lie groups which are called technically non-commutative. Okay, and why we bother about Lie groups? Because many symmetries in physics are described by Lie groups. Physics is a story about symmetry and symmetry breaking. You see, so this conference has probably taught you that. So, and many of these symmetries, most of them are generally Lie groups. This includes example of Lie groups include the Galilean group I mentioned earlier in Newtonian mechanics, and Lorentz group of special relativity, which leaves the, Maxwell's equation invariant. So Lagrangian, so you all know that the Lagrangian is the key thing in doing physics. And Professor Hoodboy was mentioning that one professor who didn't believe in climate change and who said, write me a Lagrangian. So it is that important. You see, I'm still curious to know from him privately who that professor was. Okay, I hope he will tell me that tonight. Okay, so Lagrangian constraint has to respect these symmetries of the space on which they are built on. And they can have additional symmetries as well. So any continuous symmetry, remember Lie groups are continuous symmetries. They describe continuous symmetries. So for any continuous symmetry of the action, again, Lagrangian and action, those who are not familiar, are kind of the same thing, except that there is an integration involved. There is an associated conserved quantity, and this is known as the Noether theorem. So we want to know things that don't change, conserved quantities. So for example, translational symmetry, like if the physics law or Lagrangian is translation invariant, then there would be conservation of linear momentum. Rotational invariant likewise would be conservation of angular momentum. Quantum theories likewise has Lie groups, like you heard the word SU2, SU1 many times, and these are essentially Lie groups. And as well, these are, in addition, these are called internal symmetries of the theory. They, in addition, they have their associated and corresponding conserved quantities as well. Okay, and of course, these are Lie groups. So now come to the other part, other aspect of my talk. Again, these are all background thing, and I'm emphasizing so that you take some point home. So what is general relativity? General relativity, as I said, is described by Riemannian geometry. So if I use the simplified version of Riemannian geometry, that M is a space called a space-time. Space is a common term. Well, technically, it's a manifold, and in 4 dimensions, it's a 4-dimensional manifold. G mu nu is a Lorentzian metric. Again, one of its eigenvalue would be negative, rest positive, just like in special relativity. And the curvature of this space-time is described by this equation. R mu nu minus 1/2 R G mu nu is T mu nu. T mu nu you are familiar with. This is the energy angular momentum tensor of the space-time. That is actually the reason we have gravitons spin as 2. Anyway, so this equation, Einstein initially wrote this equation in a wrong way. R mu nu equal to T mu nu, he wrote, like a lover of symmetry and simplicity. And then he simply fixed it very soon as well. Anyway, this is the famous Einstein equation. And you have to understand, to put this relationship, you need physics. That's where physics come in. Riemann would not have been able to do that. He's giving the language and the general language to write it down. Now, what is this R mu nu? This is a rank 2 tensor. If you don't know what tensor is, just take it as a generalization of vectors, So like just imagine, vector with 2 legs or something like that. And this R mu nu comes from contraction of a more rank 4 tensor, which is called Riemann curvature tensor. And that Riemann curvature tensor come from these gammas. And these gammas contain second derivative of our original G mu nu metric tensor that we are talking about. This is not fixed for like a curved space-time. In a flat space-time, all these derivatives would be 0 because that would be plus and minus 1s only. Yeah. So this is basically second-order differential equation in G mu nus. And as Professor Sen already mentioned, that there are 10 of them, highly nonlinear, 10 of them because these are symmetric tensor, and these are the most like a nonlinear physical theory. GR is the most nonlinear physical theory. And immediately after this, Einstein was able to explain the perihelion of Mercury with this and predicted the bending of light and eventually found universe expanding and black holes and Big Bang all coming from these. All these are impossible in the Newtonian theory. And as an aside, remember Emmy Noether's famous theorem that I mentioned earlier was primarily worked out. She was invited to Prague, and she worked out her famous theorems, which became a permanent thing in physics. Primarily was motivated by GR. Okay, now let's come to some simple examples. The first, so this is highly nonlinear. So Einstein thought his equations are unsolvable. So even when we have vacuum, meaning no matter meaning T mu nu is 0, yeah, there may be matter away from the space we are interested in, but it is still called vacuum as long as we are not within the matter. Yeah, so this is a vacuum solution of Einstein equation. So when it is vacuum, this whole Einstein equation becomes a very simple one. This R mu nu, Ricci curvature tensor is equal to 0. There is a process called contraction. You can show that. That means vacuum solution. So this is the simplest solution, well, this is the first solution that Karl Schwarzschild sent to Einstein, and Einstein was surprised. Watch out that if I have m equals to 0 in this is nothing but the Minkowski metric we talked about earlier, except that we have written, this in polar coordinates, this part, this Euclidean part in polar coordinates, sorry. Yeah. So, okay. So again, this is the basis, like any metric, of doing all calculations, distance calculation, curvature calculation, whatever you want. And Schwarzschild did a very clever trick to convert that nonlinear PDE system, partial differential equilibrium system, into like just a simple ODE system that could be solved very easily. You have seen this kind of coordinate transformation, meaning using right coordinate, make life simple, try to solve your favorite, quantum mechanics exercise, or not so favorite, try to solve hydrogen atom in Cartesian coordinates. You would see it would be really impossible to do. Yeah. Okay, so now solving Einstein equation, Einstein was very elated to see that it can be solved. At least one solution was found. So in general, Einstein equation is hard to solve analytically or numerically, except without strong simplifying assumption, like spherical symmetry, as in the previous example. And another most important thing, the Einstein equations are diffeomorphism invariant, meaning coordinate transformation is not going to change it. So a new solution you might think I have just found is nothing but the same solution that someone else found in a different coordinate system. Like this, take this example, again, two-dimensional Euclidean metric. This one is the same as dr squared, r squared, d phi squared. If you do the r cosine theta, r sine theta coordinate transformation that you are immensely familiar with. Okay, so to get a picture out of Einstein's solution of the space-time, one of the first few things you need to do is to understand the space-time that you have obtained in a coordinate invariant way. And, so again, to understand the geometry, you need, and ironically, it is often done by studying the solution in many coordinates. Yeah, this helps resolve problematic issues like, the Schwarzschild horizon. I want to mention here that you see this Schwarzschild metric breaks down at r equals to 2m. This becomes 0, this blows up, so it breaks down there. So is it a real problem of that space-time or an artifact of this coordinate transformation, of using this very useful coordinate, otherwise useful coordinate? So for example, here as well, this coordinate, in this coordinate, polar coordinates, r equal to 0, this goes bad. But we know r equals to 0 is nothing but the origin. And when you look this one in the light of the Cartesian coordinate, nothing wrong at x equal to 0, y equal to 0, because dx squared, dy squared passes through them. They don't get to 0. Okay, and coordinates have, when it comes to physics, has quantum ramifications as well. So Minkowski metric you can write in this, slightly different form, which is called Rindler coordinates, and this has quantum ramifications. Like you must have, or I'm sure you probably have heard of, Rindler horizon for accelerating observers. Okay, so exact solution following Einstein, Schwarzschild solution, many exact solution was found, but and today we have a collection of them, and there is this famous textbook here, second edition, that has almost all exact solutions, and how to classify them together. A catalog, a very thick catalog of them. Yeah. No, I didn't put down. Okay, I would then fast forward. So I want to tell, just since I have very little time, and this is a much longer talk, I would still would try to give you fit in within that time how to think. So the problem is, while physics was using Lie groups in particle physics and other places, the original purpose of Lie groups, the original way of Lie groups came into being was Lie was trying to solve differential equations. Okay, and that fell into obscurity, that use of Lie group. Okay, so, and general relativity was the ironic sufferer because this period of oblivion overlapped with the active era of exact solution, finding exact solution in general relativity. Funny still because we were using Lie groups, physicists were using Lie group. And then Lie's original ideas was revived in the 60s. Yeah. And then it came to the attention of many physicists, including the author of that famous book. He was surprised that such a method existed. And he took it upon himself to give lectures and write a book, and this is an excerpt from the book. If you have time, try to read that at some point. Okay, but smart people were working on finding exact solutions. So Bookdahl found that a Ricci flat metric, meaning a vacuum solution of Einstein equation, from this one can find another vacuum solution if there is a hypersurface orthogonal Killing vector field. Again, Killing vector field are isometries, meaning symmetries. For example, take an egg, rotating around the axis of symmetry and draw the curves around this, the roundish curve. Those would be like in the vector field that those curves define on the egg would be the Killing vector fields of the metric on the egg. Okay, and then there are some other examples. So again, skipping forward, we would be talking about axial asymmetric static solutions in vacuum, which is more general than a spherical asymmetric solution, like Schwarzschild we mentioned earlier. So this was vigorously studied, to cut the long story short. This system was vigorously studied, and a rigorous understanding of the mathematical structure was obtained. So we were really surprised that when we found a hidden Lie symmetry, well, first of all, you can see that if you go back to this equation has two parts in it. These are the Einstein equation. There are only 3 of them here. Of course, there are 10, but they overlap. So you see this is a linear part, and this k is the nonlinear part. If I know u and k, I know this whole thing, the metric. So u is linear, so any linear combination of u would would be a solution of this one, but then finding that k would be difficult, from those old u's, because they are not linearly related. K is nonlinear. Okay, so look, that equation is also invariant under this symmetry, meaning u naught k naught. If u naught and k in those equations, if I rescale them like that, scale them like that, the equation remains unchanged. But the metric does change, which means you obtain a new solution. So with that, we were surprised that there was another, despite the huge study that this system has undergone in the 70s and 80s, there was another explicit Lie point symmetry, that will remain unnoticed. And this is practically that. Again, no point going through the detail, just know that this was a surprise. Yeah. Okay. Now, when you write in a different, more complicated general form, that Lie point symmetry that I mentioned can give you, starting from a metric like this, will give you a complicated metric like that. These gammas are not photons. These gammas are parameter, going from negative infinity to infinity, meaning starting from a seed metric, you can get a complete one-parameter family of solutions without having to solve Einstein equation, because you have found a hidden symmetry in the set. This hidden symmetry is not the symmetry of that space-time. This is separate, like the internal symmetry of the quantum field theories. Okay, and then again, cutting to their formal process, I wouldn't have time to go through them. And it has been also, we have also generalized it to higher dimension, which is pretty surprising, because in higher dimensional Einstein equation, there is no split between linear and nonlinear part. Yeah. Okay. I'm done nearly. So, and then I want to quickly tell you, just in a minute, that this is what is famously called the C metric. C metric describe two accelerating black holes which are separated, causally separated. And this symmetric have, what is called conical singularity, which is a no, you cannot have singularity. And Ernst gave a prescription how to remove those singularities. First of all, he took a charge symmetric, put it in an external electric field, and that resulting solution became known as the famous Ernst solution. And he removed those conical or nodal singularities that appear in the original symmetric. Likewise, he immersed in an external gravitational field, and this is where we did some work as well. So, and that metric, when he immersed in an external gravitational field, it was unclear what happened. because people differed on the consequences, whether for what value of the parameter that conical singularity go away. So we revisited that. And we revisited that in a coordinate system that was invented only in 2003. We are talking about GR 2003 is a very recent time. And that helped us find the correct value of the parameters for which this will go away. And fast forwarding again, these are the exactly correct value of the parameters and periodicity of the phi coordinate of the C metric. With these two, K and C, this C metric, this is again, the letter C, nothing to do with the word C metric. This is just a constant. Okay, so we were able to do. So now, quickly, C metric was traditionally used in the 90s and the decade following that to describe pair creation of black holes. I mentioned that it describes two black holes causally separated. So in doing so, they couldn't use the original C metric because that has conical singularity. They used different ADS, extended asymptotically anti-de Sitter symmetric and other symmetrics where there was no conical singularity, or the Ernst solution, in electromagnetic field. So with this, and all this depend on if you can get a Riemannian solution out of the symmetric called gravitational instanton. And we found that, again, fast forwarding, that with the K value and C value that we have found, there indeed for a particular value of K and particular value of C, and when mass and acceleration of the C metric is precisely located, related by 1/6, the mass times acceleration is 1/6, we will have a gravitational instanton. And that gravitational instanton has topology S2 cross S2 with a point removed because of there is a singularity. And that is expected. Otherwise, we will have a compact gravitational Ricci-Flat instanton with continuous symmetries, which is impossible. So instanton with such topology, again, as I mentioned, appear in various matter and cosmological constant. And these instantons represent, again, as I mentioned, just to tweak it, represent quantum mechanical creation of black hole pairs connected by a wormhole. So this is very new result. So I am skipping the Ricci-Soliton part. We don't have time. So I want to conclude that, although a system is very vigorously and rigorously studied, don't shy away from asking new question on that. You may get lucky. And in that process, you would be exposed to some good work, a very vigorously studied field. So I have this catch that there are more Lie in Einstein equation than meets the eye. Many people who would read that, they would think that there is a lies in Einstein equation. No. Yeah, this is Lie group. Yeah, thank you very much, and sorry, and thank you for your patience.
Can I?
Sorry, one very fast question.
Okay, yeah. What are the astrophysical conditions under which you can have this pair creation of black holes?
So the astrophysical condition here is that you have to have those background field fine-tuned, basically, alpha and M. So yeah, well, first of all, as soon as you have that background field, which is, there is a certain background here. If you have that background field precisely, of course, you can have black holes which will have that particular alpha, that particular M, whose product is 1/6, would create, spontaneously. That is the understanding of Euclidean quantum gravity's approach to this. So that's it. It could be quite probable if given right condition.
Okay, so I think we can have other questions over lunch.
Yeah.
So I'd like
Feel
to
free
thank
to reach out, please.
Professor Akbar and all the speakers for very nice talks. I'll hand it over to.
Participants, we are already late. So you will get 30 minutes for lunch. And after that, we hope to start at 2 p.m. Thank you.